So the topic of today's discussion is your electrical degree and mechanical degree in rotating electrical machines. So we want to just find out that in what way or in what respect this electrical degree and mechanical degree are going to differ in case of rotating electrical machines. Although you are already accustomed to this particular relationship which says that theta electrical equals to P by 2 into theta mechanical, but I just wanted to give even more detailed description of this because the reason is that if we are going to make a formal derivation of this particular relationship between electrical and mechanical degree, then this will help us in order to derive the expression of induced EMF in a coil. So let me just show you that in this particular diagram you can view that it is depicting a two-pole structure. I mean to say both the stator and rotor, they are non-salient. Non-salient means they are cylindrical or round as far as their geometrical shape is concerned. So we have got a cylindrical rotor, we have got cylindrical stator core also. So both the structure, both the stator core as well as the rotor core, they are round or cylindrical in shape. And of course the view which you can see right now on the screen, this view is the cross-sectional view. That means we are thinking that the stator core and the rotor core of the rotating machine has been cut out by a plane, and the plane is perpendicular to the axis of the cylinder. Actually, these two concentric cylinders, I mean to say the outer cylinder is the stator core and the inner cylinder is the rotor core. So these two concentric cylinders, they are having a common axis. That is the reason why they are called as concentric cylinders. Concentric cylinder is used, the word concentric cylinder is used to emphasize that the axis of these two cylinders is the same. That means they are having the same axis. And of course, the axis is passing through the shaft. So what you can think of is that a slice is being made. That means you think that the stator core and rotor core are being cut by a plane, the plane being normal or perpendicular to the shaft axis. So this will be your the cross-sectional view. So what is saying is that a portion of the cylindrical structure will be protruding out of the screen, and the another half of the cylindrical structure is at the behind of the screen. So we are taking that cross-sectional view. So what you can see here, that the coil which is placed on the stator core, they are carrying current dot and cross. You may follow the mouse pointer please. So you can see this particular conductor on the stator core is carrying dot current, whereas this particular conductor on the stator core is carrying cross current. So depending on this dot and cross, which is shown as the direction of current which is carried by the coil. Of course, this coil is placed on the stator core. So this coil side which is on the right, this coil side is carrying dot current, and the coil side on the left on the stator core, I mean to say on the left hand side of the stator core, this is carrying cross current. So you can just apply that right hand grip rule. Right hand grip rule says that you need to grab the conductor with your right hand such that the thumb is pointing in the direction of current flow, and thereby you rotate the four fingers, then you will get the direction of the magnetic lines of flux. So you see here, dot means what current is leaving the screen, and cross means current is entering into the screen. So what you can think that there is a conductor, actually there is a coil side, but a coil side is actually a conductor only, because you can view the coil as a set of conductors. That means you have certain number of conductors on one side of the coil, you have certain number of conductors on other side of the coil. So that's what I am saying, that this conductor is carrying dot current. So you grab the conductor with your right hand. You need to think over that you are grabbing an holding the conductor with your right hand, and the thumb should point out of the screen. Why the thumb should point out of the screen? Because it is carrying dot current, so current should leave out of the screen, so your thumb should be also pointing out of the screen. So then you just rotate the remaining four fingers of the right hand. You will see that the direction of rotation of the right hand is along the direction of the magnetic lines of flux, which is indicated. So if you just draw the pattern of the magnetic lines of flux, what you will find is that the north pole is developed on this part of the stator core, that is on the upper part, and on the lower part of the stator core, south pole will be developed, because south pole is that portion where lines of flux will be entering inside the stator core, and likewise north pole is that portion where lines of flux will be leaving the stator core. So that is the way it is. Now what can you think of is that the distribution of the flux in the air gap periphery. Of course, there is a small air gap which is kept between the stator core and rotor core. So we keep a small air gap between the stator core and rotor core, so that the rotor is free to rotate inside the stator core, because rotor is meant for rotating. Now yes, we need to take care. What we need to take care, that when we are keeping the air gap, or rather when we are deciding upon that what should be the length, what should be the length of the air gap between the stator core and rotor core. So there we should actually try our best to keep the air gap between the stator core and rotor core as small as mechanically it is permissible. So what is our focus? Our focus is that we will keep a air gap between the stator core and rotor core, no doubt, because air gap has to be provided between the stator core and rotor core. Then only the rotation of the rotor is possible inside the stator core. However, care should be taken. We should be careful enough. We should be careful enough that the length of the air gap between the stator core and rotor core should not be too large. That means it should be small as mechanically it is possible. This is simply to minimize the magnetizing current which is needed for setting up the flux in the air gap. You can easily view on the screen that the magnetic lines of flux, they are leaving the stator core, they are crossing the air gap, they are entering the rotor core, again they are leaving the rotor core, again they are crossing the air gap, again they are entering the stator core, isn't it? So you see, magnetic lines of flux, they are leaving the stator core, crossing the air gap, entering the rotor core, again they are leaving the rotor core, again they are crossing the air gap, again they are entering the stator core. So you see, magnetic lines of flux, they need to cross the air gap. So if the length of the air gap is minimized, in that case the reluctance which is offered to the magnetic lines of flux is also reduced, and that will ensure that the magnetizing current which is needed for setting up the magnetic flux, that is also to a minimum. So in order to minimize the magnetizing current, you may also call it to be the exciting current or the field current. So for minimizing the magnetizing current or exciting current or field current, it is advisable that we should keep the air gap length as small as mechanically it is possible. Now what I want to say is that if you think of the intensity or the strength, let's say strength, if you just measure the strength of the magnetic field in the air gap, that means you move along the air gap periphery. Now you see, for identifying or locating a point in the air gap, we can take the help of space angle theta. So this space angle theta is going to be quite useful and very helpful in order to pinpoint or locate a particular point in the air gap periphery. So let's say that this particular axis which is fixed on the stator core, and this axis which is fixed on the stator core, it is passing through that coil side which is carrying the cross current. So over here we define theta to be 0 degree. That means what? Please follow the mouse pointer over here. If you have a point over here, please follow the mouse pointer. if you have a point over here, so this point in the air gap will be defined by theta equal to 0 degree because it is on the reference axis. Likewise, this point in the air gap periphery, please follow the mouse pointer. This point in the air gap periphery, this point in the air gap periphery will be defined as theta equals to 90 degree. And likewise, this point in the air gap will be defined as theta equals to 180 degree. So what do you find? That with the help of this space angle theta, it is very easy to locate or identify a particular point in the air gap periphery. Only you have to know the value of the angle. I mean to say you need to know the value of the space angle theta, and that will let you identify very accurately that which point we are talking about. So this space angle theta is defined such that we can able to locate or we are able to identify any point along the air gap periphery. So what can we do is that we can think of one thing is that is there any particular variation of the strength of the magnetic flux density along the air gap periphery? What I mean to say is that let's say I want to plot a graph. So what will be the axis of the graph? Say along x axis I will plot the theta, that is the space angle, and along y axis I will plot B. What is B here? B is your magnetic flux density. So if you decide that yes, we are going to know the nature of space variation of magnetic flux density, that is B. So what you have to do? You have to choose two axes. Of course, x axis will be termed as the theta axis, that means the space angle, and y axis will be termed as the B, that is magnetic flux density. Okay, so if you plot like that, so what you are going to see actually, you must have remembered that from our earlier discussion of the classes, it was found that the nature of space distribution of MMF is like this. It is actually rectangular in nature. However, if you look closely at this waveform, so this waveform is not sinusoidal, it is non-sinusoidal. Okay, it is non-sinusoidal, agreed. But it is periodic in nature. It is periodic. So it is open to Fourier series application. So since this waveform is periodic in nature, so you can apply Fourier series. So of course it will have one fundamental component and it will have your harmonic components. Let me just indicate you over here. Let's see. You can focus on this particular diagram. What is shown here? It is shown that the MMF distribution is your rectangular in nature, but we have applied Fourier series, and by application of Fourier series expansion, it is possible to express this rectangular MMF wave into a summation of large number of sine wave. Out of this summation of large number of sine wave, that sine wave which has got the same time period as that of the original non-sinusoidal wave, that sine wave will be known as the fundamental. So you can find here that the blue curve is the actual distribution of magnetic flux density or MMF along the air gap periphery, this blue curve, and this red curve is the fundamental component. So from where this fundamental component is coming into the picture? This fundamental component is coming because we are applying what we have applied. We have applied Fourier series expansion. We have applied Fourier series expansion to this rectangular MMF wave. Yes, I do agree that besides this fundamental component, there will be other sinusoidal components also, which are known as harmonics. But those harmonic components are not indicated in the diagram. Only the fundamental component is indicated. So how do you actually identify that this is the fundamental component? This is identified as fundamental component because the time period of this sine wave and the time period of the rectangular MMF wave are the same. So that's why it is termed as the fundamental component. And of course there will be harmonic components which are not indicated or shown in the diagram. So what can you do is that you can think of that this variation of magnetic flux density in the air gap periphery, variation of magnetic flux density in the air gap periphery will be sinusoidal. Now when we are saying this, that variation of magnetic flux density B in the air gap will be sinusoidal, then of course we are assuming that harmonic components are absent, only the fundamental component is there. That means actually the variation is like this, but we have applied Fourier series, so there will be one fundamental component and there will be your space harmonics. So we are ignoring the space harmonics and we are only thinking of the fundamental component. So we can now say that the distribution of, or rather we can say that space distribution of magnetic flux density in the air gap for this two pole arrangement is sinusoidal in nature. So if it is sinusoidal in nature, it will must have some zero, it will must have some positive peak, it will must have some negative peak. So what to do? Let us take the convention that if magnetic lines of flux are leaving the stator core and they are entering the rotor core as well, so it will be taken as positive. So what I am saying, let me repeat once more. If the magnetic lines of flux are leaving the stator core and entering the rotor core, then that flux will be taken as positive. So the obvious reason is that negative flux will be that flux which will be leaving the rotor core and entering the stator core. So by this convention, you can readily figure out from the diagram that flux under the north pole will be taken as positive and flux under the south pole will be taken as negative. Why? Because under the north pole you will find that lines of flux are leaving the stator core and they are entering the rotor core. So it is positive according to our convention which we have adopted in the beginning. Likewise under south pole, reverse is happening. That means lines of flux are leaving the rotor core but they are entering the stator core. So we are now in a position to exactly confirm that flux distribution under the north pole phase, I mean to say the north pole which is developed on the stator core, so that will be your positive, and flux distribution under south pole will be negative. Now what is the point or axis where value of B, that is magnetic flux density, will be 0? So that is your this point, that is theta equal to 0 degree and theta equals to 180 degree. So at these 2 points, theta equal to 0 degree and theta equals to 180 degree, you will find that the value of B, that is magnetic flux density, is 0. Whereas it is having positive peak at theta equals to 90 degree and it is having negative peak, at theta equals to 270 degree. So this was the distribution of B, that is magnetic flux density in the air gap for this two pole formation on the stator core. So let us now think of this particular case. So you can view on the screen that 4 poles are developed on the stator core right now. So what has been done? We are using 2 number of coils. Earlier there was only 1 coil, so there were 2 coil sides. Now you can see there are 4 slots. These 4 slots are created on the stator core. So these 4 slots are accommodating 2 coil sides of 2 separate coils. A coil side has got a coil has got 2 sides. So if the number of coil sides is 4, then the number of coils will be 2. So you have 1 coil which is placed like this at a distance of 90 degree along the stator core periphery, and this is another coil which is again placed at a distance of 90 degree along the stator core periphery. So for this 4 pole structure, actually the previous diagram which we have seen here, this particular diagram is depicting 2 pole structure, and this particular diagram is depicting 4 pole structure. So now for this 4 pole structure, you will be as usual able to plot the magnetic lines of flux by applying that right hand grip rule. So you can plot the magnetic lines of flux by applying the right hand grip rule. So you will find that over here, please follow the mouse pointer. Please follow the mouse pointer. Over here, north pole is developed because lines of flux are leaving this pole face. So this has to be north pole. Likewise, over here, the lines of flux are entering the stator core. So this will be your south pole. Over here, again, you see lines of flux are entering. Over here, lines of flux are again leaving the stator core. So this will be your north pole. Over here, lines of flux are entering the south pole, are entering the stator core. Lines of flux are entering the stator core. That's why this is your south pole. So in this way, we can form this north-south, north-south. So you can figure out now that there are 4 number of poles formed. Now, for this kind of arrangement where you have got 4 number of poles, you can still find certain points along the air gap periphery where flux density value, that is the value of B, that is magnetic flux density, will be 0, and certain point it will be maximum, at certain point again it will be 0. So let us not change our convention. That means the convention, whatever convention we have adopted for the previous case, when the number of poles created on the stator core was 2, let us stick to that convention only. So what is the convention? That if lines of flux are leaving the stator core and entering the rotor core, then it will be treated as positive. And if the lines of flux are leaving the rotor core and entering the stator core, it will be taken as negative. So by that same convention, you can find that flux under the north pole will be positive, flux under the south pole will be negative, again flux under the north pole will be positive, flux under the south pole will be negative. Now, what can you find out more is that there will be some peak point of the magnetic flux density. So that peak point will be taking place along the polar axis. So you can just follow this line which is passing from one north pole to another north pole side. So this line is the polar axis. So why this particular line? You may follow the mouse pointer, please. This particular line is known as the polar axis, and this particular axis is known as the quadrature axis. So what do you see? That there is an angle of 45 degree between this polar axis and between this quadrature axis. So how do we actually determine that this is the polar or this is the quadrature axis? You will find that along the quadrature axis, lines of flux will be neither leaving or entering. So you just please follow the mouse pointer for a brief time. So if you follow this mouse pointer, what do you find? That at this portion, neither the lines of flux are leaving or entering. So this will be my quadrature axis. Likewise, over here you see, neither the lines of flux are leaving or entering. So this is my quadrature axis. Again, over here, please see, at this point also, the lines of flux are neither leaving or entering. So this is my quadrature axis. And which is your polar axis or the direct axis? Let me say the quadrature axis is also known as interpolar axis. Quadrature axis is also known as interpolar axis. So now what do you see is that along this particular axis, please follow the mouse pointer. Along this particular axis, you will find that all the magnetic lines of flux are directed. So all the lines of flux are directed along this axis. So this is my polar axis. This is also my polar axis. So going by this discussion which we have made just now, you can find that the value of magnetic flux density at this point, please follow the mouse pointer, at this point, that is theta mechanical equal to 0, you will find that flux density B is 0, because over here you see, please just look at the point where I am indicating the mouse pointer. At this particular point, lines of flux are neither leaving nor entering the stator core. So that's why over here the value of B, that is magnetic flux density, will be 0. Now as you move along the air gap periphery, as you approach towards the polar axis, you will find that flux density has increased, and this is your positive maximum, because we have taken the convention that under north pole the flux density will be treated as positive. I mean to say where the lines of flux are leaving the stator core and entering the rotor core, their flux will be treated as positive. So this point is your positive maximum. Again here you find that neither lines of flux are leaving or entering. Please follow the mouse pointer along theta equal to 90 degree. Along theta equal to 90 degree, neither lines of flux are leaving or entering. So this is again that point where value of B will be 0. So what do you have found? That it is 0 at this particular point where theta equal to 0, and when theta equals to 90 degree, there also it is 0. Whereas along this axis where theta equals to 45 degree, it is your positive maximum. Where theta equals to 45 degree, it is your positive maximum. So in this way, if you just make half of the revolution, that means if you just move from theta equal to 0 degree to 180 degree, then you will find that one complete cycle of sinusoidal flux distribution has been completed, like this one complete cycle. I mean to say there will be a positive peak, there will be a negative peak. That is what is happening. Along this point, theta equal to 45 degree, there is a positive peak. Along theta equals to 135 degree, there is a negative peak. So if you just complete half of the rotation, that means you have just moved from 0 degree to 180 degree, you will find that two cycles of EMF has been, you will find that one cycle of flux distribution has completed. What I am saying is that if you move from theta equal to 0 degree, if you move from theta equal to 0 degree to 180 degree, if you move from theta equal to 0 degree to 180 degree, you will find that one complete cycle of flux density distribution has been completed. However, you see on the mechanical degree side, how far you have moved? You have only moved from theta equal to 0 degree. You have only moved from theta equal to 0 degree to theta equal to 180 degree. You have moved only from theta equal to 0 degree to theta equals to 180 degree. But on this distribution of B, magnetic flux density, you will find that a one complete cycle of EMF has been completed. If it is not EMF, then you can also say the magnetic flux density. So if you make one complete, if you just complete one rotation, I mean to say if you just move from 0 degree to 360 degree, so mechanically you have moved by 360 degree, but electrically you will complete two cycles of flux density distribution. Let me just recapitulate once more, that at theta equal to 0 degree, value of B is 0, that is magnetic flux density is 0. At theta equals to 45 degree, it is positive maximum. At theta equal to 90 degree, again it is 0. At theta equals to 135 degree, it is negative maximum. And at theta equals to 180 degree, again it is 0. So what do you see? That when you have moved from theta mechanical 0 degree to theta mechanical 180 degree, one complete cycle of flux density distribution, that means B, one complete cycle has been created. But if you just make one complete rotation, that means if you move from theta equal to 0 degree to theta equal to 360 degree, you will find that two cycles of flux density distribution B has been completed. So what we say, that if there is a EMF induced in this conductor, so that will be given by BLV. So whatever is the distribution of B, that will be also the nature of E, that is induced EMF. Because for this conductor which is placed on the rotor, you may find on the rotor a purple color dot is shown. So that is our conductor. It is having length L and it is moving with tangential velocity V. So what is the EMF induced in this conductor? EMF induced in this conductor is BLV. So L and V are constant because it is assumed that rotor is rotating at a uniform speed. So L and V are constant. So whatever is the variation of B, that is magnetic flux density, that will be the variation of E, that is induced EMF. So what do you see? That for one rotation, for one 360 degree mechanical rotation, for one 360 degree mechanical rotation of the conductor, two cycles of EMF will be generated or two cycle of induced EMF will be there. So from this way only we can conclude that theta electrical here equals to 4 by 2 into theta mechanical, because you can correlate that when there is a positive peak, when there is a positive peak in the value of B, that is magnetic flux density, at that point mechanical degree is 45. So that's why I was saying that theta electrical equals to 4 by 2 into theta mechanical for this particular 4-pole case. So in general, if the number of poles are P, it will be theta electrical equals to P by 2 into theta mechanical. So I would just stop over here for today.